Okay, so this is basically a very informal chalk talk or whiteboard talk on how we get information out of the HTM. Basically Matt asked me to talk about the CLA Classifier, which is going to be my main focus, but more generally, just to mention how we get information out of the classifier. We talk a lot about encoders, but then the question is how do you decode the HTM? So encoders will create SDRs for feeding into the HTM, and then HTM generates SDRs, and then how do you decode that stuff? So that's kind of the overall theme, but focusing on the CLA classifier. This is being recorded at Numenta while people are eating lunch, so this is really informal, and you might hear chomping and other stuff going on. So, but Numenta folks, feel free to ask questions at any time. What I've drawn on the board at first is just a high-level picture at first. This is kind of the typical. This is kind of the typical architecture that we work with in Numenta. So we have information coming in, scalars and categorical information, date and timestamp, GPS information, whatever data we're working with. That gets fed to encoders. Encoders convert that data to sparse distributed representations, goes through a spatial pooler. Out of that you get another SDR, and it goes through a temporal memory or sequence memory module, and out of that you get another SDR. Okay, so that's kind of how the basic flow of data, and of course this is temporal data coming in, so you have a sequence of information coming in and a sequence of SDRs. On the other end of the scale there's a bunch of applications that we deal with, so there's predictions of predicting the value at a future point in time, doing anomaly detection, so when something unusual is going on, and then and sequence classification, which we haven't done much of, but it's kind of a focus of some of our research right now. So the question is, you want to do those applications, you have SDRs coming out, so how do you go from here to there? That's the kind of the decoding problem. So we have a variety of tools in NUPIC to do that, and we'll list that stuff here. So we have the CLA Classifier. We have anomaly scores. And anomaly likelihood. We have something called the Anomaly Classifier. And we have KNN Classifier. And in NUPIC, we also have an SVM classifier. And then a long time ago, we used to do something called reconstruction. Okay, so these are the various tools we've used in the past to go from SDRs to actually connecting with real applications. The focus of my talk is really going to be the CLA classifier, because that's what Matt wanted me to talk about. I'll just briefly touch on some of these other things. Anomaly scores and anomaly likelihood, there's a really nice talk by Scott on our website, so there's a lot of detail on that already. And the rest of them are not heavily used right now, so I'll just briefly talk about it. So the focus is going to be here. A couple of points about it. These are sort of tools on how you read out SDRs and connect it with applications. These are not biological at all. They're just code blocks, if you will, or algorithms that we implemented that are not biological. But understanding how these work and why they work requires understanding the properties of SDRs and what the temporal memory is doing and what the HTM is doing. So to really understand these well and understand why they work, you need to understand this stuff as well. But these techniques are not biological. Let's see, I'm not really going to discuss the code per se. I'm just talking about the algorithm, mostly for the CLA classifier. And I think this is a basic. We could touch on the code a little bit near the end. If you have questions. Okay, any questions about that at all?
I have a question.
Go for it.
You've got, from encoders moving up to spatial poolers, SDRs, but I've heard that referred to as not necessarily sparse. The encoders don't necessarily create sparse representations.
Yeah, they don't, most of the time they are sparse, and the most important thing is that the properties we expect in terms of overlap and semantic meaning and things have to be met here in order for the spatial pooler to work.
But they are sparse, but just not as strict. I mean, you couldn't have a dense representation, like a computer ASCII code or something.
No, you couldn't have that.
And I don't think you'd want to have 50% of the bits on it.
Right.
But it's more tolerant.
Okay.
Yeah, I think the main thing is that the properties we expect of SDRs have to be met, because the spatial pooler really expects SDRs. Okay, any other high-level questions here? Okay, so I'm going to now really focus on the CLA classifier. What did I complete? Where's the stuff? Okay, so in NUPIC, we have something called a CLA classifier block. And this gets this SDR as input. And it also gets a few other things as input. So in general, if you look at what's fed in, let's say through the OPF to the encoder, you can have multiple fields. So you can have field 1, field 2. Typically we deal with 1, 2, 3, and 4 fields. And then one of these fields is designated as the predicted field. So we say, okay, this guy is going to be the field we want to predict. I'll just call that a PF. Okay. And that's an important field. And what we do is the encoders have a special output, I believe, that feeds in the predicted field to the CLA classifier. Okay? So it's getting the SDRs flowing in, and it's getting the value of the predicted field flowing in. Okay? It's also getting, so this is the actual value of the predicted field.
Oh, so not the SDR, but the value itself.
The actual value. So it might be, let's see, if predicting energy, you know, it would be like 2.3 or 10.5. Or if you're predicting category, it might be dog or something. That's what gets fed in. And then it also gets fed in the bucket index. And I'll explain why this is. But if you know about encoders, you know that different values have different buckets associated with them. And if it's a category, the bucket index is just the index of the category. And it also gets a record number. Okay, so it's like we're on record 42, and then next time 70, 43, 44, and so on. And this is also used, and I'll show you why. Okay, so what is, and then the output from here is predictions. Okay, and so I'm going to go into a little bit more detail. So what is this classifier trying to do? So it has basically two jobs. It's trying to predict the predicted field, k steps into the future. And k is a parameter that you have to decide ahead of time. So you might say, okay, I want to predict the value of this predicted field 10 steps into the future. Or if you're doing, let's say, hourly energy readings, you might want to predict it 24 steps into the future if you want to know what the prediction is going to be next day at this time.
And can we do both? Can you say like 1 step and make 10 steps at the same time?
Yeah, so the question is, can you do like multiple values of this? And yeah, you can do that. And basically what happens is internally, you get a completely different copy of the CLA classifier. But each sort of classifier instance does one step, set of steps into the future. But in the OPF, you can specify any number of them. The other thing it does is that it predicts a probability distribution over the predicted fields. Okay, so basically, the CLA classifier implements a function, so you have an SDR at time t. It's going to tell you the probability distribution of the predicted field at time t plus k. That's basically what it's doing.
Is it assuming a certain type of distribution? Like
No, it's a non-parametric probability distribution. I'll explain exactly how we get that. Okay, so and basically the way the learning works is that in order to figure out what this mapping is, it keeps track of a mapping, or keeps track of a table. So it basically says, give me the SDR, oops, time t minus k, and it learns a mapping to the predicted, updates a mapping and maps it to the predicted value right now. Okay, so it just shifts everything k steps. So this is how it actually does the learning. And so basically it keeps track of a list of the last k SDRs. And whenever it does this learning, it looks at the current predicted value, the SDR that was k steps ago, and then updates a table that keeps track of this mapping. Okay, so it just keeps a buffer. So the bigger k is, the longer a buffer it has to keep. Now each SDR is sparse, so the actual memory usage is really small. You can have hundreds of time steps, it doesn't matter. That's just fine. Okay, so let me give an example. So suppose you had sequences A, B, C, D, E, F, and you had A, B, C, G, H, I. Okay, and let's say you saw this 75% of the time, and this one came 25% of the time. Okay. So let's say you're partway through here. So let's say you have the SDR for the sequence A, B, C. Okay. What it's going to output is it's going to say, so you've seen it up to that point, and we're trying to predict one step into the future. What it's going to say is that D has a probability of 75%, and G has a probability of 25%. Okay, so it's seen this multiple times. These are the statistics, and for k equals 1, that's what it's going to predict. If you had trained it with k equals 2, let's say, anyone want to guess what? You're not laughing at that, sorry. Anyone want to guess what it should say?
E, F, A, or H, I, A?
So it's seeing ABC up to this point, and you're predicting 2 steps into the future. So what it's going to say is that
E, or
and
H.
that would, so E would happen
75.
75% of the time, and H would happen 25% of the time. Okay, because that's the only possible things for 2 steps into the future. Okay, yeah.
Is this mapping maintained in memory so you can like explore it and navigate it separately at a later time?
Yeah, these are all structures in the CLA Classifier, so you can certainly investigate all this. I mean, it has to figure this out as well from the data structures. Okay, so that's a simple example. This can also work with scalar data. So if you had, let's say you had a sequence that was a little bit of a weird sequence, but let's say you had something like this. And now you're at this point. what it would do is it would predict a value here and perhaps a value down here with different probabilities depending on how often it's seen that. And there actually might be if there's noise or just variation, there might actually be a spread of values here and a spread of values here. So it's actually a pretty, very useful output to have this probability distribution that can do completely disjoint probabilities like this.
But if it sees the sequence that is very periodic, why would it predict the one that has the high amplitude?
So if you're, so it's seeing this sometimes, seeing that sometimes. So if you're right at the top here, right? Okay, so I did it very periodic here, but assume this is noisy. Like sometimes it sees this, sometimes it sees that. Yeah, that's what I meant. Then it would do that. If it was like A, B, A, B, A, B, then if it's really learned this high order sequence, then it would only predict, hopefully the HTM would only predict one. Yeah, good point. Okay. So another question is, how do we get these numbers out? And it's actually pretty simple.
But the classifier is not doing predictions. Prediction is doing memory.
The classifier is reading out this SDR and figuring out how it maps to values that are
It's
going
not
to come.
actually doing the prediction of the sequence. That's done in the.
Well, the output.
Yeah, so the thing is, what do you mean by the prediction of the sequence? So the HTM is predicting in its language, which is SDRs, it's predicting what's going to happen next. But it's really hard for a human to read this. So the classifier is mapping this SDR. So the HTM has all of the
high order
information.
sequence is in the.
It's in the HTM,
Is
yeah.
the HTM.
And so when I said, before, that really understanding why this works requires understanding the HTM, that's exactly what you said. I mean, that all the information is in here.
Right.
This is just decoding that.
So, are we allowed to speak on this?
Yeah.
You just answered your own
The
question.
confusion
There you go.
is that the temporal memory makes predictions constantly, but we're
Yeah.
not using them at all. The intuition behind this is, we're using them in the sequence.
Yeah, we're using it in the sequence.
But not to make the prediction. The intuition behind this is that the state of the temporal memory at any point in time, the active cells, not even the predicted cells, just the active cells, is all the knowledge you could possibly have about the world in the past and in the present. There's no more additional information you can have. It's a representation that says, this represents the sequence of patterns that have come in the context of previous learning. So that's all you've got to work with. And you can say, that's the best knowledge I have about the world right now. I'm just going to classify it by mapping it to some future values in future states. And you're basically just saying, how well does this tell me what some variable is going to be in the future? Because there's no more information I could ever possibly have right now. And so it's not making a prediction in the sense like the temporal memory is making a prediction of the next step. It's a classifier classifying some future value, the current state with some future value that might be of interest to you. Very different type of prediction. In some
Yeah,
sense.
so an example of that, of what Jeff's saying is, if you look at a high order sequence, so what I showed you there wasn't really a high order sequence, but if you look at a high order sequence like A, B, C, D, E, F, and then H, oops. So something like this, so you have A, B, C, D, E, F, and H, I, C, D, J, K. This is a high order sequence. If you were right here and you had seen everything, the classifier would correctly predict J one step into the future and K one step into the future. It would not predict E and F. And that's because the SDR at this point from the temporal memory encodes all of this context, the correct context. It needs to make a unique prediction, an unambiguous prediction. Okay, so to really, because we're mapping from SDRs that are output from the temporal memory, we can handle all that higher context. Okay, anything else before I describe the actual mapping, the table mapping?
So in that example, if you just feed in the SDR from the encoder, it will predict both.
It will predict, that's right. If you don't have the temporal memory in there, in the higher order thing, if you fed in this SDR or even this SDR into the classifier, it wouldn't be able to tell, and it would predict both.
And as Subutai goes through this, realize when we design this that the system is rarely in a perfect state of anything. It's usually got a lot of noise going on. There's lots of multiple predictions. Some columns are predicted, some columns are not predicted. And so it's very rarely in some sort of beautiful, pristine state like this. So we had to be able to say, given this messy SDR, which represents a combination of some predictability and not, some knowledge and not, how do you map it?
Yeah.
And so it's never really pristine at all.
Okay, so I'm gonna need a little bit of room. I guess I'll leave that out there. So I'll draw an SDR going down this way. I'm not gonna draw 65,000 bits. So here's a typical SDR, or that let's say it's coming out of the temporal memory. I've drawn it vertically, and we've just, from the classifier standpoint, it doesn't know anything about the internal structure of the temporal memory. It's just one flat array of bits. But let's say you had 4 cells per column, then in reality this might be column 1, and this might be column 2, and so on. But it's just a flattened version. And then basically, it just keeps a mapping of this to future values. So let me first deal with the category case, because that's a little easier, and then we'll deal with scalars. Okay, so we're predicting k steps into the future. Okay. And remember, it keeps a buffer of the last k SDRs. So let's say you have let's say an SDR comes in that's 3, 8, and 12, and your category at time k, time t is D. Okay, so that's what you have right now.
3, 8, and 12 are the bits that are on?
The 3, 8, and 12 are the indices of the bits that are on. So let's say 0, 1, 2, 3, so this bit is on, 4, 5, 6, 7, 8, and this bit is on. Okay? At every bit, it maintains a table where you have an entry for each category. And what you maintain in here is a count of how often you have seen D when this bit is on. Okay, so for bit 3, this would become 1. And you have another one here. For D, you have 1. Okay, so the first time, so basically it's going to just keep a bunch of counts for each category and then normalize it all to get the probabilities. So let's say at the next time step, or at some other future time step, you get 3, 8, and 12 on again. So that's your SDR from k time steps ago, and the category is G. G. So what would happen then is the same set of bits are on. Now G would get a 1. Okay. So right now what the state of the classifier says is that if this bit is on, it's expecting D and G roughly half and half, and when this bit is on, it's expecting G roughly half and half. So as you do this over time, you'll update the counts, and if D is happening 3/4 of the time and G is happening 25% of the time, you might get, let's say, after a while, you might get something like 3 here and 3 here, so you have a 3-to-1 ratio of counts. And in general, it's going to be pretty noisy. So
there could be big numbers in there.
In general, it's going to be big numbers.
Hundreds and thousands.
Yeah. And then it's pretty straightforward. You can imagine, you can just normalize these, so you would have 75% here, 25% here, and normalize this, and then add up everything and divide by the number of bits.
But, does that mean that bursting columns are going to have more weight in terms of what's predicted?
Yeah, so the question is bursting columns. So if you have bursting columns from the beginning when it's learning, you might have these guys might, all of these cells in a column might get associated with a particular category, right? But as soon as the temporal memory starts learning, one of these bits is going to have a much higher set of counts than the other bits, right? So if those other cells are then used really for some other sequence, you might have a tiny bit of weight associated with an incorrect set, but over time it's going to wash out. Okay, so yeah, so bursting columns are just, you know, it doesn't know anything about whether columns are bursting or not. It just sees SDRs and it maintains this.
One sort of corner case would be, what if there was no learnable sequences, right? It was random associations. Then you want the system to go back to being a pure sort of point-to-point classifier. And say, well, it's a first-order classifier. It's just given this.
Yeah.
And so the way you describe it will do that. You want to make sure that it actually, in the case that the things aren't predictable at some level, that it still worked properly.
Yeah. If columns are always bursting, then you just get a certain set of columns. You just get 8 times as much. Let's say you have 8 cells per column. You have 8 times as much information for a particular pattern, but it'll just all normalize out.
Well, bursting
Okay.
column is the zero sum, right?
Mm-hmm.
It will not affect the number because everybody gets
Yeah.
a number.
Yeah, exactly. And then you're just down to the properties of how uniquely you can represent the patterns at this level.
So how do you, and so,
Yeah.
oh, you keep going, I guess. I'll just wait.
So there's one other trick that's done here, which is in practice is useful. So I mentioned that we normalize the likelihood here. So what we'd actually get is 0.75 here and 0.25. 0.75 and 0.25. The other thing that's done is that these likelihoods are actually, it's not a straight sum, it's a moving average. So it keeps track of the most recent values for each of these buckets, if you will. So basically, once you do the normalization, the actual likelihood is a moving average of the likelihood.
Is that moving average window a configuration in the model parameters?
Yeah, so the moving average window is basically this alpha parameter to the classifier. So what it actually does is gets the, for each bucket, it gets it calls the likelihood times 1 minus alpha plus, whether it's on or off times alpha, whether that category is actually present. So whenever it gets a new category associated with this bit, let's say it's D, so D is actually present here, so the likelihood for D will get improved just a little bit, and the likelihood for G will decrease just a little bit, which is what would happen anyway, but this weights the more recent values more. So going back to the question of bursting columns, again, you can see that if columns were bursting initially, but then it became predictable, that's another pressure that kind of reduces the effect of the counts associated with the bursting data. If that makes sense, because that's like, if it's learning the sequence properly, the bursting will go away for that pattern.
And is there any mechanism that increases the sort of like weights for counting for correctly predicted cells? Like in this table that you keep, if things are correctly predicted, if they have a bigger weight, then it's almost like the input of it.
Yeah, so there's no, the classifier doesn't know anything about whether it's correctly predicted or not, so it's just treating bits in this dumb way.
But you haven't talked about how you combine these different bits that are on at the moment. But
Oh, that's just a straight sum and a normalization to 1.
yeah. So one of the things that would happen, Marion, is if naturally if I have a predicted input, I have fewer bits on, right? And so those bits will have a more of each one would be more significant. If you had a whole bunch of bursting columns, then you'd have a whole bunch of these, and each one would have a lower impact on its own.
I guess I'm thinking of a situation where it's not perfect because you have some noise, so you have some columns bursting and some that you have some well-predicted cells. So in that case, even though some are bursting and some are well-predicted, you just kind of like bump up a little bit the sort of count for the well.
Yeah, so if there's noise that results in bursting columns, that will give just some counts that are spread
Right. Okay.
randomly around different bits or different columns.
Okay.
And so the predicted columns predicted cells are the ones that are going to be on more often. So those are going to have much higher likelihoods. So the assumption is that over time that'll just wash out.
You could tweak this algorithm to say on an ongoing basis, perhaps give more weight to predicted. So let's say you had a bunch of cells that were predicted and a bunch of cells that weren't predicted at one time. You could design it such that the ones that are predicted get more of a say. That'd be an interesting tweak to experiment with. We got really good results doing it this way. It's not clear up front which would be better in all situations.
And actually, I've been thinking about that this classifier could be very good when we're thinking about sequence classification. We could use the same basic technique, but then you would want to do the predicted cells would have a greater weight.
Yeah.
Because you want to learn really quickly.
Yeah.
This sort of assumes a long-term streaming predictive scenario.
And
But if you want to learn the
Thinking
quicker,
about it right now, this actually might work a little bit better. If
I
we
think it
did-
would. That's right.
Even for just prediction,
Yeah,
but we didn't do that.
no, but that's what I've been, I think for sequence classification and in general for the classifications that we're doing, this mechanism, it really exploits the properties of SDR as well.
Yeah.
So this makes sense to me from a categorical standpoint,
Yeah.
but when we start talking about output resolution of scalar values,
Yes.
how do you get to that? Is that
Great segue. Thank you. Okay, so this is categories. So how do we deal with numerical values? Scott here? No, Scott's not. He understands this better than me, so he can correct me if I make a mistake. But what happens with scalar values is that for each bit, in addition, here we're keeping track of the counts for each category. But what it'll do is it'll bucket the scalar value. So let's say you're predicting energy. It'll bucket it into a certain number of buckets, and it'll keep counts for each bucket. So
and that's divided by the bucket resolution in the
exactly. Yeah.
bumpers.
So let's say your energy value can go from 0 to 100. You might bucket it into a certain number of buckets, and the number of buckets is determined by the encoder bucket, the bucket size. So whatever resolution you set the encoders to, that's going to be exactly the resolution here. And so you basically get a histogram, for every value, what the count.
Think about it, that's not an absolute requirement. You could, it seems to me we did do it that way, but we could have bucketized it any way you want.
You could, yeah, I think we tried that too. This was nice because it's kind of inherent, the bucketing here is sort of dependent on the noise in the data. And so this was actually.
You kind of remove a parameter.
Yeah.
If you didn't do it that way, you'd have to specify what your bucketing size is, and doing it this way, we just automatically determine what it is.
Okay,
So there's one other trick. So with scalars, so this is the counts or likelihood. Okay, so now we're dealing with scalars. The other thing this does is it actually keeps track of another array, which is a moving average of the actual value. Okay, so each bucket here represents a range of numbers. And in the encoder, there's sort of a natural midpoint to that range. So you could just use that midpoint, and you can say, okay, that midpoint has a value of probability of 75%. But what we found works a little bit better in practice is to keep a moving average of the actual value that you saw when you did that. So let's say this can go from anywhere from 20 to 30. So the midpoint would be 25. But maybe most of the time when this bit is on, you actually see 29. So you can get a slightly more precise prediction, and we tested this empirically, and this works better.
That was my next question.
Yeah. Perfect.
Well, also, it could be, what if your sensor, for example, what if your sensor only output even numbers, right? And
Yeah.
but your average might be some scalar value in between, so your
Right.
prediction would not be an even number. It
Yeah.
would be just, but that doesn't really make much sense. But this way, in some sense, it'll give you what, if it actually always turns out to be between, there's 25, 27, 29 odd numbers, it'll give you 29.
Yeah. And also, yeah, exactly. So, and this is a very precise thing. It's for this bit in this numerical range. So it's actually, not that bad to do, to keep track of the actual value there. It's a very fine kind of mapping, if you will. But in practice, when we did that, our accuracies improved there. And the moving average for this is, again, it's the exact same type of calculation. It uses the same alpha, I think. So the alpha parameter in the CLA classifier, I think, is the main parameter. I think it's tuned during swarming as well.
And changing the alpha parameter changes how far back
so
the memory goes.
Yeah, exactly.
Every system, every aspect of a online learning system has to have a concept of the time over which you're concerned with. Everything has to be this. Everything in HTM theory has it. Everything in the classifier has it. Anomaly detection system has it. So this is just nature. You have to, and there's no right answer to how much prior history should you be looking at or not. So it's not something you can predetermine.
Yeah.
Well, that's somewhat supported biology also, because people have different periods of time over which they learn. My sister, she can remember back till she was 2. I can barely remember what I had for lunch today, or finishing lunch today.
There's an inherent conflict between, well, in the past I saw it work one way, but more recently I've seen it work another way. So which do you bet on, right? Do you go with historically the longer term view that it used to be like that, I'm going to go with the old version, or as you know, but a couple times recently I saw it this way, and people do differ on those kind of things. But that's the nature of the problem, and until you actually get the data, you don't really know.
Yeah.
But you can swarm over it, and that's the nice thing about it, because you could, maybe on a particular data set, one alpha would do better than
Yeah,
another.
if it's really noisy, you might want a slower alpha so that it doesn't fit to the last value quite so fast.
So the resolution also for the bucket between 20 and 30 will never predict anything other than 29 if the moving average is 29, correct?
If the moving average is 29 in here, then what that means is when this bit is on,
It will always be 29.
well, the contribution from this bit is going to be 29 times this probability. Because, and in general, you're going to have 40 of these bits on, let's say. So you're going to add it all up, averaged by the
So the
likelihood.
predicted value is not going to be 29.
It's not going to be 29.
Well, it
it's
would
gonna
be
up.
29, the world always had seen 29 predictable sequences.
Yeah, if it's always 29 for all of the 40 bits, then yeah, it will be.
But it's mostly 29, sometimes 25.
Yeah,
So it's going to be some number in between 25 and 29.
yeah, depending on what the mappings are for the other bits. Yeah, so basically, as with, just like with SDRs, each bit itself has very little contribution. It's kind of the ensemble of bits together that make the contribution. So one bit gets messed up, it's not a big deal at all.
And each bit is playing multiple votes.
Yeah.
Each bit is saying, well, sometimes 75% this, 10% that, 5% this.
Yeah, because this bit could be used, could be participated in multiple sequences, but it's extremely unlikely that all the 40 bits are together participating in 2 completely different sequences. So, in fact, very few of them would be. So it'll all wash out at the end.
So as you're adding the different 29 times 0.75 and for each of the different bits, how does it determine which bits to aggregate? So is it the most likely in each of the...
So it looks at, so what it's going to do is look at the current SDR and then predict the value, right? the current SDR is gonna have, let's say, 40 bits on. So it's gonna look up those 40 bits, look up the table for those things, and add it all up together. And I don't remember if it was the exact, whether it's this multiplied by this and then added up, or if these are added up separately and averaged. I don't remember the exact calculation.
Yeah, I guess it's the mapping function that I'm curious about, because my 0.75 for bit 3 there,
Yeah,
0.75 might be 29. For bit 8, 0.75 might be 76.
okay, so
how do you
let's go
deter-
through that, yeah, let's
Yeah.
do that. So let's say, well, it wouldn't be,
Because
so
they're
this guy-
two separate, totally separate sequences, right? So the most likely next value in
so
for
this one might be
bit-
21, let's say, for between 20 and 30, and this is,
Oh,
let's say, between
right, 'cause
40.
it's based on the bucket. I'm sorry.
It's based on the bucket.
Now
right?
now I'm with you.
Yeah, so
Okay.
50 to 60, so you can see it's pretty
Yeah,
robust.
yeah, okay.
So let's say 50 to 60 here,
Yeah.
just 0.25, and
I
maybe
understand.
this is like 56, and this is, I don't know, 52.
Yeah.
So I don't remember the exact calculation that does, but the basic prediction, if you only had these two bits on, would be, let's say, an average of 21 and 29. Would be one prediction with a probability of 75%, and an average of 52 and 56 with a probability of 25%. So that's what the actual prediction. And there are a couple of different ways you could do it. If it's a weighted sum and then a normalization or not. I don't remember the exact. Okay, but you can see the overall algorithm is really simple. At the end of the day, it's just table lookups.
That alpha thing tripped us up for a while to get that to work right, but.
Yeah, there's some optimizations, like you don't have to update the likelihood for everything every single time. If you just keep track of the record number, then you can, it speeds things up a little bit. So there's some code optimizations there.
So that,
Yeah.
maybe you just mentioned it, but what if, because you have noise, instead of having in the second, for the second bit 75 and 25 in that order, maybe it's switched between the two things?
Yeah, that could happen.
So then
Let's say
what
this is
the-
25 and
the output of
yeah, so this is the exact, here's where the exact calculation actually matters, and I'm not sure which one. So it could be that it's still 21 plus 29 over 2 times, 0.25
or maybe more like a weighted
plus
sequence.
0.75 over 2. It could be like that. Or it could be, I don't know if it matters.
It doesn't wait, right?
21 times, so that's one possibility, or it could be 21 times 0.25 plus 29 times 0.75.
Seems more likely to be that way.
It might be, yeah. I think I remember discussing this with
And you wouldn't divide by 2.
back then, and we tried both ways, and they actually didn't matter, because there's so much robustness.
But, Mary, it doesn't have to be because of noise. Remember, these bits are participating, as Subutai said, in multiple sequences. So it's really a very complex set of numbers that you can't, it would be very common to have different values like that for the same buckets, but not because of noise, just because the variation in the data and the different sequences are represented. And
Yeah.
so it's this sort of this really crowdsourcing voting methodology going on.
Yeah, it's really an ensemble. Each bit
Yeah.
is just a tiny little classifier, and it's a voting method across all 40 of them.
That's a good way of looking at it, as an ensemble.
It's an ensemble.
An ensemble method.
Okay, so a few things about this. One is, as you can tell, you need to decide k in advance, and you can have multiple values of k, and for each value of k, it creates a completely separate table like this. Okay. You can see it potentially could be memory intensive, and in practice, the classifier is somewhat memory intensive. It's almost as similar to the temporal memory in general. So it is pretty memory intensive. But in general, these values are going to be pretty sparse. So the implementations take care, do take that into advantage. So we tried a bunch of different methods as well. This method works really well. in a lot of data sets that we tried. And so, maybe it's because of the ensemble properties, because of the SDR properties and so on. But I've benchmarked prediction, let's say, against ARIMA, which is a very well-known, state-of-the-art kind of time series prediction method. And for the data sets that we work with, this works a lot better than ARIMA, particularly as you get further and further into the future. ARIMA can also predict for K-steps in the future, but this does really well when you do that. ARIMA kind of loses track of the predictions. So this works very well. ARIMA cannot do multiple predictions at a time. It can't handle this probability distribution of a prediction. So this is something that this can do that it can't do.
That's an important point, because the output of this is a distribution of values.
Yeah.
And very often in a situation where someone wants a prediction, they have some objective function, which is the value they can extract from acting on a prediction. And by having a distribution of predictions, you can determine whether you should take a particular action. So it may be, for example, if something was predicted with a 60% likelihood, it's worth doing something. But if it's predicted with a 45% accuracy, it's not worth doing.
Yeah, so a good example is, let's say you're trying to predict the probability of an earthquake. And if you just take the most likely one, it's not going to be an earthquake. But let's say so normally the chance of an earthquake is, let's say 0.001. Or for some reason tomorrow, there's a 1% chance of a really bad earthquake, right? But still, the most likely prediction is no earthquake. But knowing that probability, we would completely change the way we behave if we knew there was a pretty good chance of a really bad earthquake tomorrow. So that's an example of where knowing the distribution can really affect your decision.
This is a very common thing in business schools.
Yeah.
It doesn't have to be something as rare as an earthquake, but lots and lots of decisions are based on objective functions, which have put a value on different percentages of the likelihood of something happening. So having that distribution is very, very important.
A couple other things.
Question.
Yeah, go ahead.
So how do you determine alpha? It's like, it seems to be data sensitive.
Yeah, so we typically do it by swarming. In Grok for IT or whatever, we've just found that it's a fixed value works.
So it's a fixed value.
Yeah. Actually, I take that back. Alpha is not used in anomaly detection. This is only for prediction.
Okay.
So, right. So, if you really are trying to optimize accuracy, you might want to swarm.
There's a swarm logic.
But we didn't do any investigations into that. For example, there's a lot of things we used to swarm over we don't anymore because we find it doesn't really make that much of a difference. And we don't really know. Maybe alpha here could be, we might find there's a couple of values or one value that works really well.
No, we did look at that with the
did
energy
we?
stuff. Yeah, and Ellery way back when he did his study, the clusters included alpha. Because that was for prediction, not for anomaly detection. Yeah, so pretty sure that for most problems, you're not too sensitive to this. It's just sort of extreme cases. And if you're really trying to get really optimized accuracy, then you want to do that. This is tied in, the CLA classifier is tied into the swarming mechanism as we've talked about, so that's there. There's both a Python and a C implementation of this. So the C implementation is the fast one, obviously, and it's called Fast CLA Classifier. And what else? As you can see, it can handle both categories and scalar values, which is also a really nice property. One place people have gotten tripped up before is that it's really designed to be predicting this predicted field, and you're assuming a stream of data coming in. And most machine learning problems are not set up that way. They're set up as spatial problems where at a particular point in time, you're predicting a value at that same point in time. Here it's predicting into the future. And in the typical machine learning cases, you would have a holdout set where you don't give it the predicted field at all, and you ask it to do the classification, and it's not really set up well for that, at least in the OPF. You could imagine setting it up so that the predicted field is not fed in here, it's fed in separately, but that is not in the OPF today. So it's really designed for streaming scenarios. Okay, any other?
I have a question about, you said none of these techniques of extracting information from an HTM are biologically plausible, correct? Including the CLA classifier. What would be the biological equivalent of classification then?
Yeah, so, I mean, a biological equivalent would be, you're shown, a stream, like a data stream, and you're asked to say, okay, what's the next thing? And you say, 2.3, right? So in that situation, what's going on is it's a lot more complicated. You have multiple hierarchies, you have multiple sensory modalities, you have invariance that's going on, so you look at the pattern, you have some, invariant representation of what the next thing is going to be. A little while later, you figure out how to unroll that into a motor sequence that gives you, so it's very different.
So does that mean, when we get to the point of hierarchy, that there will be no classifiers in between the layers?
So if you have a hierarchy, how does this look? You would not put classifiers in between, but you could still use the CLA classifier at the top of the hierarchy to read things out.
I actually would argue that biologically we're not good at this. We're good at predicting the next thing, hearing the next note, knowing what you're going to hear or feel. That's the next thing. That's the prediction from the temporal memory. But if I asked you, are people really? So let me see, make up an analogy here. Maybe trying to think of something like. I do some sequence in the morning, and how well does that predict something's going to happen in the afternoon or something? I don't think actually we're very good at this. I don't think we're able to take a sequence of patterns now and correlate it to some future prediction based on the actual order in which things occur now. I think you have trouble finding examples of us doing that. We tend to do more simplistic future calculations, like not take advantage of the time, and more of a sort of a classic sort of classification. I would argue that biology doesn't do this very well. And what we did here was, the beauty of what we did here is we said we have a system that actually can really discover the great state of the world right now, and we'll give it a memory that human memory doesn't really exist, which is to keep track of all the things to state in my brain right now and map it onto some future value in the world tomorrow or something. And I don't think biology does that in any way. I think this would be better than humans.
Thank you.
The couple other things I wanted to say, not about the CLA classifier, is in the past we used to use reconstruction to do that. So instead of taking the SDR and running it through this mapping, we used to take the SDR and try to feed it back through the spatial pool of permanences and try to figure out which encoder bits corresponded most to that prediction. That kind of worked, but this works a lot better. And in particular, when you have multiple possible things, the multiple possible next steps, this can give you a very nice bimodal distribution or trimodal distribution or whatever. If you run it through the spatial pooler, it all sort of gets smushed out, and you don't make very good predictions. And of course, this can give you actual probabilities or likelihoods, which you can't get easily this way. So that's one thing. For anomaly detection, we don't use the CLA classifier at all. We just take the output of the temporal memory and we look at the predicted cells and the actual active cells and see what the difference was. And Scott has a really nice talk on anomaly scores and anomaly likelihood that you can listen to on them.
We do have to do something somewhat similar in the sense we have to keep a history of anomalies over time, and there's a concept of a moving average of anomalies, and which might be similar to the alpha here.
Yeah. So that I didn't want to go into the details, but Scott has gone.
Yeah, no, I'm just saying
right.
there's a similar level of complexity in doing anomaly scoring as this here. It's just different.
There's also something called an anomaly classifier, and that's used in the following case. It hasn't been heavily explored, but the code is there. I think it's actually broken right now in the OPF because we made some changes to the way anomalies are calculated. There's an anomaly class, and I don't think it hooks in. I think that piece is actually broken. But the basic idea there is if you see an anomaly, the CLA or the HTM is a continuously learning system, so it's going to over time learn that anomaly. But if that particular pattern is one that leads to something really bad and you want to remember that, then you want to store the state of the SDR so that later on you can classify it. In that case, we just use a KNN classifier. So we take the SDR that's coming out of here, and it keeps track of a buffer of the last n SDRs, and you can say, okay, 100 time steps ago there was something really bad. Remember the SDRs that were in that time range and store it in a KNN classifier. So that's what the anomaly classifier does. Okay, I think I'll probably stop.
I have another question.
Yeah,
Sorry.
go for it.
So it looks from your...
That's why I said probably stop.
From your graph here, it looks like if the encoder's responsibility is nothing extraordinary. It's just the predicted field, bucket index, record number. That's not something that someone who is writing an encoder would need to deal with at all. Is that correct?
Well, the encoder has to output bucket index. So it has to have a concept of buckets in order to
Right.
work with the CLA classifier.
Okay.
And that's used to figure out what these is.
So I'm just wondering, if I'm writing an encoder, let's take the coordinate encoder, for example, because currently from what I understand, there's no way to get predictions out for an coordinate encoder. My question is, why is that and what's missing?
Yeah. That's a complicated question. So it's not clear to me the CLA classifier as is would work well with that.
We treat
'cause
each coordinate as a bucket.
you could treat each coordinate as a bucket.
It's just not a fixed number.
Yeah, so we just have to figure out, you'd have to make some changes into how this table is calculated.
Yeah.
Like the concept of taking bits and mapping it to values would work fine, but the exact data structure here, I think, would need to be a little bit.
One of the complications would be in the coordinate encoder, each bit can at any point in time represent different ranges, and
Right, but that's the same, that concept is true for scalar encoders too.
well, except here
Oh, each of this bits, yeah.
Well, it's just a
Exactly. There's two
tweak.
levels of this.
There's a
yeah.
tweak to it you'd have
Yeah,
to make
Yeah,
that
that's
work.
right.
The concept, as you said, should work, it just needs to be tweaked.
But this would be a great project for the community. If you understand how the CLA classifier works and why it works, and you understand the coordinate encoder, that would be a really nice project to create a geospatial classifier or something that works specifically with.
That'd be really cool.
In theory, it should work very well. There's no reason why it shouldn't work.
You might, a simple thing might be, instead of an actual value here, you'd have X, Y, and Z, you might have 3 different tables. That'd be a really simplistic version of this. So you have 3 stable values, and you determine the resolution of that based on the resolution.
But the coordinate encoder is n-dimensional.
Let's say GPS encoder.
Okay.
X, Y, Z, N, there you go.
But yeah, so this could be an n-dimensional structure, which would just make it, a little more memory, but maybe that concept would just work fine. And it would probably do decently.
Have you ever thought about doing equivalent to NAB with prediction?
Like a benchmark?
Yeah.
We've thought about it, we haven't done it yet. But that would be a project.
I think the way we've done these things, they're breaking new ground. I don't think anyone's ever done this kind of prediction before on time sequence, or done that kind of anomaly detection before on time-based sequences. And we had to invent a lot of stuff to do this. And it works really well. So, I gotta believe in the future, people are gonna wanna make predictions about future values.
Yeah.
So.
Yeah. No. Well, yeah. In the future. I think that, again, this would be a really nice thing if the community wanted to do it. We could do it too, but a proper time series benchmark for streaming data, not for non-streaming data.
We could bounty some of this stuff, like the coordinate classifier. That'd be really useful.
Yeah, I'll give $10 for that.
Okay.
But yeah, that would be a great, really nice thing. So right now, for the GPS stuff, you can only do anomaly detection, but once you have a classified version, maybe you could just extend this to the n-dimensional.
It'd be great for gaming.
I know.
If you had a series of moves on your opponent,
well, that's
and
what
you
I
wanted
was
to predict
thinking.
where they're going to be 3 seconds in advance or something like that,
Right.
and you'd get a distribution.
Good for AI.
You get a distribution where the likelihood of that agent's going to be and then you can make the calculation of the cost of shooting something. I don't play games, but I'm making this up.
Sure.
The cost of shooting, I assume, so, and you could do it as an objective function, and you could optimize your likelihood of your game.
I know you play Call of Duty in your office.
I've never played a first-person shooter.
All right, so I've got one more question.
Okay.
With the random distributed scalar encoder,
Wait, hold on.
with the random distributed scalar encoder, each bucket could have different resolution windows. So you could have, the
No,
bucket could be 20 to 30, but it could also be, because you're randomly distributing.
no, the buckets are fixed resolution in the RDSE.
Yeah, no, you're saying a bit
You're
could
gonna
represent a
have
different
n
range as
number
well.
of, yeah, you're gonna have n number of buckets, and each bucket is gonna have multiple different
Oh,
resolution
oh.
windows.
Oh, okay,
encapsulated.
they won't have different resolutions, but they'll have different windows. Yeah.
ranges.
Different
So
ranges,
you can
yeah.
just extend
So
it.
it might be 20 to 30, and it might also be 790 to 800. Right.
Yeah, so in the RDSE, what we did is the bucket index, it still works exactly like the scalar encoder. So a given bucket index always corresponds to a fixed range.
Okay.
So as you increase the, as you go beyond, you add more values that it hasn't seen, it just creates more buckets on the fly.
Okay.
And it just keeps appending here.
So you just
And
have a
the
longer,
classifier
you
is
just have a longer array there of buckets.
just a longer array.
Gotcha.
And the classifier is designed so that if it sees buckets it hasn't seen before, it just expands the array.
Okay.
So it can deal with that.
Okay.
The only thing I had to do there was to make sure that we never have negative buckets. Because the classifier doesn't know how to deal with that. It's just an implementation thing, so as long as it starts at 0, it can keep expanding.
Negative buckets.
Yeah, because in
Buckets with
RDSE
a
you can
negative array.
expand both ways.
Yeah.
Right, so you could end up with negative bucket indices.
Yeah.
And so I just put a max on how far you can go. So the bucket indices, I think, actually start at like 500 and go up and become 500. It's super. But it works. To the classifier, it looks almost identical to a scalar encoder.
Okay.
With a GPS encoder, it's multidimensional, so it's a
Yep.
little bit different. Buckets can grow in all these directions.
Okay.
What, maybe I'm missing something, but why can't each bucket be one coordinate? And you'd have a lot of buckets, because you'd see a lot of coordinates, but as you see more coordinates, it would add more buckets.
You could do that, yeah. You would have to do it for this scheme to work. But because you have X, Y, Z, a person's trail could go all over the place. So you have to have some scheme to create ever-increasing bucket indices as you move to new locations. And then does that make sense? So every time you create a new bucket, if you will, you have to keep track of that bucket index and that location, so that if the person comes back to that location, you output the same bucket index here. If that makes sense. Maybe I didn't
Why
understand
can't
the
we,
question.
if we index this by the coordinate, so like, could be like X, Y, Z, J, whatever, so this is one, this corresponds to a bucket, and you could find the bucket given this coordinate,
Yeah,
and then each of these buckets would be like one of these coordinates.
yeah.
And you just keep this is a number of how many times this coordinate was visited when that bit was on.
Yes, the only thing is this is a range, not an absolute.
It's not, no, it's an absolute number.
No, because if your resolution is, let's say, 100 feet, then if you move 1 foot left or right, it should come to the same bucket.
No, the coordinate encoder is each coordinate is an integer. It's an integer coordinate system.
Oh, okay. Then you could do, yeah. Then you
So,
could do it.
yeah.
So this is not GPS then?
No, this
is the
is
internal coordinate. Yeah, I got it, yeah.
So GPS is mapped onto the integer
Yes.
coordinate system.
Then you could do that.
So that way, you wouldn't have to change, because you just said that you can add buckets on the fly.
Right.
Already in the
Yes.
classifier. So.
But it expects an integer index.
Well, you could just hash this.
Yeah, that's exactly what I say. You can hash it as long as you
You have to keep track
of it, and you don't want it to give huge numbers out all the time.
Yeah, I see.
So I think it would be, I think it would be, I think it'd be better if you just modified this to directly use something like this.
You could potentially end up with an unmanageably large array.
Yeah,
Have memory
and-
issues and things like that.
Yeah, so there's some implementation things, I think, to be optimal and fast, because updating these things can be slow if you don't do it right.
But the other, what we also wanted to work with, if possible, work with the existing API system. So you don't have to change anything. When you specify that you want prediction, it just works.
Yeah, I mean, that's desirable, but I think it's more desirable to have it work well and fast. So if you have to change the OPF to get it working well and fast, I think that's okay. You don't have, the overriding constraint doesn't have to be, don't change the OPF.
Thanks, Subutai.
Okay, thanks, bye, new pick.
Bye.